Hello everyone, welcome to another physical sciences lesson. A topic we're investigating electromagnetism. Today we're going to be looking at a different slant to this topic, and we're going to be looking at what is electromagnetic induction. It might be sounding quite complicated, but actually it's very interesting and it's very useful too. So let's have a look at it. So electromagnetic induction is the topic that we're looking at, and we recognize it's got a component of electric current. That's what we would like to get out at the end, but it builds on the process of magnetism and how these two are linked. Now remember, previously we have linked these two together by saying where there is an electric current, we can produce a magnetic field. Now, we're going to be looking at the opposite process, or the converse process. Can we use magnets to create electricity? And that's the first question that I want you to think about. So, how can you generate a potential difference across the ends of a conductor without using a battery? Now, I've already given it away, in a sense, because we'd recognize that to do this, we don't need a battery all the time, but maybe we can use a magnet as well. And maybe you've seen those sort of torches that have got magnets in them that you shake and you can get them. Well, that's exactly the principle that we're looking at here. If you look at a bicycle as well, you turn the wheel and you'll find that the light on the bicycle goes on. It's the same principle. But let's dive into it and let's see what it's all about. And to start with, we're going to be revising some key terminology. So the terminology that I want us to look at today is the word potential difference and the word EMF. These two terms are very similar to each other, but they're very important in this context. And so I want us to look at potential difference. When we've been dealing with electric circuits, we know that potential difference is defined as the work done per unit charge between 2 points in a conductor or a circuit. The symbol for potential difference is V. It's measured, the SI units are volts, and the symbol for the word volt is also V, and the equation is V is equal to W, the work done, divided by Q, the charge. And so what you need to recognize is when we're dealing with potential difference, it's really the source of electrical energy that we've got to make a circuit work. Because remember, in a circuit, the requirement for a circuit for charge to move is we need a potential difference, we need a complete circuit that is closed, and we need that closed circuit to be made by conducting wires. So those three requirements are what allows us to use electricity and to measure it in an electric circuit. Now, that's not the only way that we can work out potential difference. We can also use Ohm's law. Now remember, Ohm's law is the way that we relate potential difference, current, and resistance to each other. And the equation that we've got to work out potential difference is simply this one, where we say V is equal to I times R. I sometimes forget it and I get all confused. It's on the data sheet in a different form, but I remember it because it spells a word in Afrikaans, the word vir. And so if you've ever done any Afrikaans, it might be a memory trick for you to remember the word potential difference is V is equal to I times R. It spells the word vir. Right. Now, how do we measure potential difference? This is really important because it's all very well knowing the terms, but we want to actually measure it. And there are different instruments that we use to measure potential difference. And the list is this. It's something called a voltmeter. A new instrument that we're going to come across is called a galvanometer. And the difference between the voltmeter and the galvanometer is simply where you put the zero. So on a galvanometer, you can have a negative part and a positive part, and the needle can go to the negative part. The zero is in the middle, but it could also go to the positive part over there. That's in the galvanometer. And of course, there's the multimeter. Multimeter is a digital device, but we can do exactly the same. Now, when we're looking at a voltmeter or a multimeter, remember, whatever the instrument is, we always connect to measure potential difference. The connection is in parallel. So we must make sure our connection is in parallel. Now, just to make sure that we've got this all sorted out, here's a circuit diagram with a battery in it, a voltmeter, and it's measuring in the closed circuit a potential difference. I want to just quickly look at the simulation, and let's see if we can get it up. Right, on the simulation, we recognize the voltmeter is reading 1,0 volts. The EMF of the battery is 1.5 volts, which is the same as what we've had before. What I want you to see is if we change the battery around, and now we make the positive terminal on the left-hand side, we'll see that the voltmeter, the multimeter here is reading negative 1.50. So in this case, the current direction is in the opposite direction to which the voltmeter is expecting. The voltmeter is expecting the black terminal to be the closest to the positive side and the red to be closest to the negative, and it's in the wrong direction. If I switch the cell again, now you'll see from the positive terminal, it's coming from the positive and away at the negative, and so it's reading a positive value. And so reading potential difference is really quite important. We recognize that the terminals of the voltmeter or the multimeter or even the galvanometer are important because it could be a positive or a negative. It just tells us something about the expected direction of conventional current. Right, I think we've more or less laid the foundation for this section. There's just one last thing that I want to mention, and that is this idea of EMF. EMF is the maximum. EMF is the maximum potential difference that a battery or an energy source can supply to a circuit. And we're going to need to make sure that we are working with EMF as much as possible. And we're going to get used to doing that as we look at this principle of electromagnetic induction. So take a short break, and we'll be back to explore this in a little bit more detail.